Welcome to this video. My name is Mark Zithian. The date today is November 27, 2024. This video is going to focus on how to make accurate and safe bungee jumping calculations. So the first step is that we have to convert the jumper's weight in pounds to kilograms mass, followed by converting the altitude from feet to meters, and then using the metric system gravitational acceleration on Earth 9.81 meters per second squared, a constant value. So the next step is to then compute the jumper's gravitational potential energy in joules. So this is the product of multiplying the jumper's mass times gravitational acceleration times the height. And so when we carry out that calculation, we compute 118,856 joules of gravitational potential energy of the jumper prior to the jump. So this is also equal to 87,394.12 foot-pounds of gravitational potential energy. So then we'll write that in at the top of the bridge here. Next step is to access the elastic potential energy equation. So elastic potential energy U is equal to 1/2 the K constant of the bungee cord times the change in X, or the stretch distance of the bungee cord, that value squared. So that is the elastic potential energy. So essentially, bungee jumping is when we transfer the jumper's gravitational potential energy before the jump into the cord in the form of elastic potential energy. And so there is some free fall velocity prior to the bungee cord stretching. So not all of the jumper's potential energy is expended, but some of it is converted into kinetic energy. And the idea is to gradually absorb that kinetic energy into the bungee cord in the form of elastic potential energy. So then it's a gradual distribution of kinetic energy into potential energy, but instead of resting on the top of the bridge, now the potential energy is transferred into the bungee cord. So the dynamic force is reaching a negative value and decreasing to 0, so that if this was not a bungee cord, it would just snap and break, or injury would occur to the jumper if it didn't break. So that's the difference between a regular cord or a wire and a bungee cord, is that it's gradually absorbing partial kinetic energy from gravitational potential energy into elastic potential energy, and by the time it comes to a rest, we're reached then a static tension of the bungee jumper's weight. So we have a 450-pound max tension limit, but that's a static tension after everything comes to rest. So that is the aspect of bungee jumping calculations that I've noticed concerns some people making these kinds of calculations. But tracking the sequence of events prior to starting the engineering physics makes the process clear and seamless, so everything can be accounted for, and this then translates to reality, what happens out there in the real world. So we focus on the elastic potential energy equation. Again, U, elastic potential energy, is equal to 1/2 times the bungee cord's K constant times delta, or change, of the cord stretch, X, that quantity squared. So all we have to do is start with the input energy. So identifying the conservation of energy, we cannot create or destroy energy, we can only change its form. So if there was not a bungee cord, all of the jumper's potential energy would convert completely into kinetic energy, and reach a maximum velocity right before impact, but then that would not be bungee jumping. That would be a lethal activity. So that's why we're controlling this with partial kinetic energy distribution, then returning the total energy from gravitational potential energy into elastic potential energy. So from the jumper's potential energy, some of it converted to kinetic energy, and then that initial value, 118,856 joules, then transferred into the bungee cord in the form of elastic potential energy rather than the gravitational or jumper's potential energy. So all we have to do is realize that the energy is constant, and it is with respect to the input energy, so that is the GPE made equal to the elastic potential energy. We identify the K constant of the cord, and so that is the K constant in newtons per meter. The U value is in joules, the potential energy, and then the X value is the bungee cord stretch in meters. So now all we have to do is solve for X. So now we have 1/2 of the K constant value. Then we simply divide the GPE into 7.6. So that is equal to the change in bungee cord length stretch squared in meters. So then we solve that ratio and we find the square root of the value to cancel X squared into just X. So this becomes 125.06 meters of bungee cord stretch. Then we'll convert this into bungee cord stretch in feet. So then if we subtract the bungee cord stretch from the altitude, we still haven't cleared the safe hang altitude, but we know it's 89.8 feet. So 0.8 feet is approximately rounded up to 10 inches rather than 9.6 inches for safety. And so then the next step is to subtract the safe hang altitude of 20 feet from that value. And we get 69.8 feet, or 69 feet, 10 inches of unstretched bungee cord is then harnessed and fabricated into the bungee mechanism connected to the secured eye bolts on the harness of the jumper and on the standing level of the bridge. So next we have the free fall time and maximum velocity prior to initial cord stretch. So there will be some free fall time involved, and that is a distance, a vertical distance equal to the unstretched bungee cord. So we can use the delta D sub Y, or the vertical distance with respect to free fall, which is equal to 1/2 GT squared. So we start first by converting the 69.8 feet of free fall equal to the unstretched cord length. 69.8 divided by 3.28 is the meters of free fall distance. 21.28 meters, then made equal to 1/2 G, or 4.905, then times T squared. So if we solve for T, we just divide 21.28 into 4.905, and this becomes 4.34 is equal to T squared, and then we get the square root of 4.34 to solve for T. So this becomes 2.1 seconds free fall time prior or before initial bungee cord stretch. So the last calculation here is the maximum free fall velocity prior to initial bungee cord stretch. So that is just the V is equal to GT. This is the free fall velocity with respect to gravitational acceleration times the time of free fall. So when we multiply 9.81 meters per second times 2.1 seconds, so we get 20.6 meters per second. We then convert that to feet per second, 67.6 feet per second. This is the maximum free fall velocity prior to initial cord stretch. And then we can convert this into miles per hour for some familiar reference. It's 46.1 miles per hour of free fall maximum velocity prior to bungee cord stretch. So now we've accounted all the different sequences in the kinematics and dynamics to secure a safe and reliable calculation. So the last step is to use 1 gallon water jugs for the testing. Each gallon of water weighs 8.33 pounds, so if we divide the jumper's weight 175 pounds into 8.33, that is 21 jugs of water, then tethered with just a regular rope and then connected to the bungee cord, placed at the standing elevation on the bridge, and then moved out over the open air and without any movement released, so that vector goes downward. And we're assuming we don't have any crosswinds or updrafts. And then when the 21 gallons of water negotiates the bungee distribution and comes to a rest after a little bit of bouncing, if the jugs are 20 feet above the ground or approximately that altitude, then the test has been completed as success. This can be repeated several times, and that also tests the cord and the eye bolt junctions with respect to the harness and the eye bolt on the bridge. And so then one last point is that terminal velocity will not be an issue because the altitude is too minimal to negotiate any standing boundary layer that would then be a aerodynamic drag upward. It would just happen too fast. So you could use the terminal velocity equation at the final velocity right before the cord starts to stretch, or you could just use the drag coefficient times the air density and times the projected frontal area on a denominator, and then the weight on the numerator, its square root, but then it would just be outside of the limit. So ruling out terminal velocity is it is actually very intuitive, but I ran the calculation and that's very redundant, so we don't have to worry about aerodynamic drag. We may have some concern with crosswinds, updrafts, but if it's a pretty mild to steady day, the jump will happen so fast that it's really negligible. But it is worth mentioning, at least that came up. But one thing I noticed about making these calculations when teaching physics classes or consulting with various clients and customers is that there was this kind of this, I wouldn't say this wrong intuition. It is a good intuition that how could you have such a low maximum tension rating, 450 pounds, when obviously there is going to be this dynamic force that builds up in free fall before it transfers to the cord, the bungee cord. But that is why it's a bungee cord. It gradually converts the kinetic energy at pre-stretch into the stretch of the bungee cord, thus distributing a relatively negative value or decreasing value of dynamic force. So there is dynamic force at the end of the free fall, at the end of 2.1 seconds, but it is gradually absorbed into the bungee cord and then distributed in the form of delta X, or the increased stretch of the bungee cord. That's why it's a bungee cord. It's designed to graduate the dynamic force until it goes to rest and it becomes static. So all you're really dealing with is 175, give or take 10% pounds on that cord. So you're about 2.5 times safe, or 2.5 times greater in static tension limit compared to the jump parameters, or the jump weight parameter of the jumper. Thank you for watching this video and have a great day.